I'm also gonna lock the meeting.
Okay.
So pretty.
Okay, awesome. Just making sure. Cool. Thank you guys.
Also, I can hear us. independently. I want to thank you all for being here today. We always enjoy having people at our shows. And if you're watching asynchronously, be sure to hit the subscribe button so that you know when we're actually going to go live and you'll get those notifications. I want to lay down some ground rules before we start. Just be considerate in the chat, but feel free to drop your questions at any point during either of the talks, and I will field them to the speaker at the end of each talk. And with that, we'll go ahead and get started with our first talk, so that way we don't have to wait. Our first speaker is a graduate student in astronomy at the University of Wisconsin in Madison. In his undergrad, he majored in astronomy and theater, and in his theater career, he once had to teach a nun how to fight. Here he is to tell us about his work in stellar evolution. I want to present to you Andrew Nine.
All right, thank you, Courtney, for that wonderful introduction. So, like Courtney said, I'm going to talk to you about my research here at UW-Madison. And I'm going to start off my talk with this story. Now, this is a story that's been told lots of times before, but it does bear repeating. So it starts off with a cloud of gas floating in space, and then at some point, that cloud of gas begins to collapse. And as it collapses, the center of that cloud gets hotter and hotter until it gets so hot that it ignites and becomes a star, like our sun. And then this star will fuse hydrogen into helium in its core for several billion years or so, until at some point the hydrogen in its core runs out. And at that point, it expands into a red giant. It can swell up to around 100 times its original size. And at this stage of the star's life, it is no longer fusing hydrogen and helium in the core, but it still does so in a thin shell around a now entirely helium core. And then this phase will last for a few million years or so, until at some point the outer layers of that star get expelled and it leaves behind, it gets expelled into this beautiful planetary nebula, and what's left behind from here is a white dwarf, which is the core of the star that once was, what currently weighs about half of the original mass of the star for a star like our sun, and is now about the size of Earth. And it will then cool off over the next several million years. Now, I'm sure you've all heard this story lots of times before, but this is, of course, astronomy, and this is science, and not just storytelling. So the question of the hour is, how do we test this? Which is a fair question. I mean, the answer to this one is we go and observe stars. Lots and lots and lots and lots and lots of stars. Now, it would be just dandy if there were a whole bunch of stars that all formed at the same time in the same place under the same conditions. We could test all of our hypotheses, and hey, look at that, we do. Now, there are groups of stars in our galaxy called open clusters. And these open clusters are clusters of stars within our galaxy that all formed at the same time from the same initial cloud of gas. So they're all made of the same stuff. The only difference between any two stars in an open cluster is their mass. And that's really important because the mass of the star determines almost uniquely the time it will live. Now, a typical open cluster it usually contains about a few thousand stars. And we think there are about 5,000 of these open clusters in the galaxy. Now, of these 5,000, we've studied maybe 1,000 or 2,000 of these at all, and most of those we haven't studied in any great detail. Now, on the right side here, this here is a picture of a very famous open cluster that we call M67. Now, to the untrained eye here, this cluster looks like a bunch of stars. And to the trained eye like mine, it's a bunch of stars. But if you look really closely at that cluster, you'll start to notice some differences between the stars. Some of these stars appear a little more red, some of the stars appear a little bit more blue, some are brighter, some are dimmer, and all those features in the stars carry really important information. And we take all that information about the colors of the stars, how bright they are, and we can put all that together into a diagram that looks like this. This is called a color magnitude diagram. And there's a lot going on here. And we'll go ahead and take a little bit more time on this one. So on the horizontal axis here, this is where we keep all that color information. So the further to the right you are here on this diagram, the more red the star is. And the more to the left the star is, the bluer, and therefore the hotter it is. And on the vertical axis here, this is the magnitude, or how bright the star is. So the further up the scale here is, the brighter the star is, and the further down, the dimmer. Now you'll notice there is a really clear pattern here in the stars of this cluster. So this feature here is what we call the main sequence. And this is where stars spend the bulk of their lifetimes. This is where they're fusing hydrogen into helium in their cores. And over here, this is the giant branch. This is when all the hydrogen has been used up in the core and the star expands and gets way bigger. And this point here is the cluster turnoff. This is just at the point when the stars have finished burning hydrogen in their cores and they're almost going to turn into a red giant. Yeah, so it's really tempting to look at a diagram like this and say, oh, okay, so the star forms on the main sequence, makes its way up, loops around the turn off, and goes up the giant branch. It's really tempting, but that's not what's going on here. What actually happens is that a star will form, find a spot in the main sequence, and it will sit there for basically its entire life. And what will happen over long periods of time, this cluster turnoff will move down the main sequence. So if you know the distance to the cluster, and if you know where the cluster turnoff is, that will tell you exactly how old the cluster is, and therefore how old all of the stars are. And that would be a really great test of our understanding of stellar evolution. There's just one teeny tiny little problem. When we point our telescopes at open clusters and take note of how bright all the stars are, and how blue or how red they are, we don't quite get this diagram here. We get this. Now, if you look really closely, you might notice there are some pretty glaring differences between the old plot and the new one, namely this whole bunch of stars up here. Now, these stars, according to our understanding of stellar evolution, they should have evolved already. They're too bright, they're too massive. So why are they there? Well, if you look, it turns out if you look at these stars a little bit more carefully, you'll notice that almost all of those stars are in binaries. Now that's key. So what are binary stars? Well, in this sense, it's kind of obvious. They're two stars orbiting one another. And they typically form at the same time from the same cloud of gas. So again, really the only difference between these two stars is how massive they are to begin with. And you can divide binary stars into two broad categories. One of them are visual binaries, where if you point a telescope at them and you can resolve the two of them individually, those are visual. And on the other hand, we have spectroscopic binaries, where if you point a telescope at them, you cannot resolve the two of them individually. You have to rely on other means. And most of our work here at UW-Madison focuses on spectroscopic binaries, because these binaries tend to be physically closer together. And if they are close enough together, they can interact. And when they do, a lot of interesting things can happen. For instance, we form such stars as blue stragglers that are over here, bluer, blue on the main sequence, blue relative to the main sequence. We also have the yellow giants and the sub-subgiants, and last but not least, the blue lurkers. Now, most of my work here focuses on the blue stragglers up here, so I'll spend most of my time talking about those, but I'll also touch on the yellow giants and the sub-subgiants here in just a little bit. So, what are blue stragglers? So, blue stragglers are stars that are bluer and more luminous than the cluster turnoff. So, in this particular cluster, there's a group of them here, brighter and bluer than the cluster turnoff. There's also a handful that are simply bluer than the turnoff. And we think that blue stragglers form through three primary channels, which are mass transfer, stellar collisions, and the merger of an inner binary. So, first things first, let's talk about mass transfer. So this happens in particularly close binaries. So in this particular setup, we have a star here in the center that is still on the main sequence. It hasn't evolved yet, it has not expanded. And its companion over here off to the right, it's a little bit more massive than its companion, so it has evolved first. So as it expands, eventually those outer layers get so tenuous and is close enough to its companion that those outer layers get ripped off and it gets deposited onto its companion through this matter stream here. So what happens in a setup like this is you'll have a star that's way bluer and way hotter given the age of the cluster than it should be. And it'll be spinning rapidly, and there'll be a white dwarf companion. So the leftover core of this star here orbiting way out there, usually several tens or even 100 or so astronomical units, the distance between the Earth and the Sun. And so, yeah, if you see a really rapidly rotating star and a really wide binary, the star kind of looks like a white dwarf, odds are some mass transfer process happened there. Now, it'd be really great if we can get a picture of this in action. Unfortunately, that's really difficult, so here is an artist impression instead. So you can see here the red giant, the outer layers of that envelope getting ripped off and deposited onto its main sequence companion here. You can see it's actually getting hotter and more massive as it accretes that matter. All right, now let's talk about collisions. So collisions are interesting because it's actually a really common problem given to graduate students in astronomy. If you're considering how often any two stars in the galaxy will get close enough to even strongly interact with each other, let alone collide, turns out it never happens, ever. You'd have to wait something like 10 million times the current age of the universe, and I don't get that much telescope time. However, if you do the same problem with a binary star instead, it turns out it's a whole lot more likely. So this particular simulation I'm about to show you isn't meant to represent any one particular star, but it's simply one avenue a collision can take place in. So what's going to happen here is we're going to have this initial, actually a triple star system instead. So you see there's orbiting in some stable configuration, they'll orbit, and then they'll encounter another binary system. And one star gets ejected right away, and the rest will go through some chaotic dance until they collide. And what will eventually happen is they'll find a new stable configuration to orbit in. So those two more massive stars will start orbiting each other, and that little yellow star will get ejected off into space, and now we have a brand new binary with a blue straggler in it. And then we have our last channel of formation, which is the merger of an inner binary. Now, this one's a little bit more complicated, so bear with me. So in this particular setup, we have a binary star system here in the center. These two stars are orbiting each other. And then there's another companion orbiting the central binary, but much further out. Yeah, so this diagram doesn't make it all that clear, but this star here is orbiting both of these stars simultaneously. So what can happen here is if this star here is orbiting this inner binary in just the right way, it can drive these stars either further apart or closer together. And it'll drive them further apart, then closer together, then further apart, then closer together, until eventually they get so close together that they just straight up merge. And they become one star where there were once two. So now that's how we form blue stragglers. Now blue lurkers, yellow stragglers, and subgiants all form through much the same way. So first up we have the blue lurkers. Now these are really new in terms of stellar astrophysics. These were only discovered within the last year or so. So blue lurkers, we think these form the same ways as blue stragglers, but they're less luminous. They don't get quite bright enough to stand out in a color magnitude diagram. So the only way you can really pick these out as of now is through rapid rotation and wide separation. So yeah, see that rapidly rotating star with a white dwarf companion, odds are good that mass transfer has happened and you have a blue lurker. And then we have the yellow stragglers up there on the right. Now, yellow stragglers, we think these are just evolved blue stragglers. I mean, these are still stars, and they do still evolve. So when they do, they'll move, instead of moving up and to the right, they'll just move more straight towards the right, and they'll eventually merge with the rest of the red giant branch. And then we have the subgiants. Now, subgiants are much less luminous than giants or subgiants, so they'll end up right over here, way to the red of the main sequence. So these stars, again, there's not a lot known about these right now, but we think they form either through mass transfer, dynamical interactions like the collisions we saw earlier, or really intense magnetic fields. Now, to give you all a little bit of insider information here, whenever an astronomer starts talking about magnetic fields, that's usually code for we have no idea what's going on. And this right here is no exception. So how do we study all of these stars? So my work here at UW-Madison is part of the WIN Open Cluster Study, or WOCS for short. Now, let's see, breaking down this acronym here, the W here is for Wisconsin, I is for Indiana, the Y here is, of course, for Missouri, and N here is for the organization formerly known as the National Optical Astronomy Observatory, or now it's called NOIR Lab. Yes, so this here on the left-hand side here, this is a picture of a telescope that I use to conduct all my study as part of all of my observations as part of the study. This is the WIN 3.5-meter telescope, which is located out in Tucson, Arizona. On the right-hand side here is a close-up of the telescope itself. And this black circle here on the side of the telescope, this is the heart and soul of my work. And what that is a spectrograph, but it's a very special kind of spectrograph. Before we get to that, however, I'm going to talk a little bit about spectroscopy, because this right here, believe it or not, is a picture of the sun. Yeah, so you've probably done this, something like this in your science classes, where you take sunlight and you pass it through a prism and you end up with a rainbow on the other side. This is very similar, but if you break that rainbow of sunlight down enough, you'll start to see these dark bands appear in the lights. And those bands of darkness, those are caused by the elements that are present in the sun's atmosphere. So for instance, let's take hydrogen, the most abundant element in the sun by far. So hydrogen, you might call as one electron around it. So whenever sunlight encounters a hydrogen atom, if that photon has just the right frequency, just the right amount of energy, that electron will absorb the photon and jump up. And that photon is just gone. And then sometime later, that electron will jump back down and it will release the photon, but again at that very particular frequency. So because the hydrogen there is present in the sun's atmosphere, that electron will absorb this particular frequency of light, this particular wavelength. And you'll end up with that dark band right here. It's, in this case, 656 nanometers. But it also has absorption features. It also absorbs particular wavelengths of light here at 486 nanometers and a few other wavelengths besides. So every element does the same thing, but because every element has different numbers of electrons, they'll all absorb light at different frequencies. So if you know where the bands of light occur in the sunlight or in the starlight, then you know what elements are there. So how does spectroscopy work for me as part of WOX? Well, remember that black circle? That there is the Hydra multi-object spectrograph. So this right here is a picture of the inside of that particular spectrograph. So in this circle here are a whole bunch of fibers that we can place directly on top of where the star appears on the sky. And at the end of each of these little fibers is a little button, which you can see a little bit, we see a close up here on the left-hand side. So the starlight will enter the top of the button. It'll hit this 45-degree angle mirror, and it'll go down the optical fiber. And it'll travel down to a special room in the basement, go to the spectrograph, gets broken up into its component wavelengths, and then we end up with an image that looks like this. This here is 100 stars all lined up next to each other. And this is actual data that I have worked with. So you'll see here, these dark bands running across the image, those are those absorption features, that much like what we saw earlier with the sun. Now, if you look real closely, you'll notice that not all of those spectral features, not all of those lines line up with each other. You'll notice there's a bit of a squiggle if you go across the image. That is key. So if you're all familiar with the Doppler Shift, which is the same physics when you're on the highway and there's an ambulance coming towards you, it's the sound of the siren will sound higher, and once it passes you, it drops in pitch, it sounds lower. Exactly the same thing is going on here. So if we're looking at a star, what we're tracking is what we call its radial velocity. That is how quickly it is coming towards or away from Earth. So what we're looking for is a spectral feature that at some point in time appears blue shifted as it's coming towards Earth. It gets higher in frequency and shorter in wavelength. And then at some time later, it's moving more away from Earth. So that same spectral feature will then appear redder. Its wavelength will lengthen and frequency will decrease ever so slightly. And what we're looking for is that feature to come back and forth, back and forth, back and forth. And that is the sign that we have a binary on our hand. So we keep tracking that back and forth shift, and we try and figure out exactly how those two stars or orbiting each other. So, yeah, I mean, all these stars that I've described sound pretty exotic. So, question I like to think about, like you to think about for a moment is, how many of these stars do you think go through these alternative pathways? Do you think it's more like 1 in 1,000, 1 in 1,000,000, 1 in 1 billion, perhaps? Could be very rare. Keep your guess in head, because I guarantee you, you're way off. Turns out, if you're looking at all the evolved stars in open clusters, turns out it's more like 1 in 4. 25% of all of the evolved stars in these clusters have gone through these alternative pathways. They've interacted with a companion, and they've gone and done something different than our understanding of stellar evolution would otherwise predict. So these stars are not strange by any means. They happen all the time. So a few quick points of summary here. So stars in binary systems can go through alternative pathways in evolution, including forming blue straggler stars. And blue stragglers can form through different channels, namely mass transfer or interactions with other stars and binary systems. And binary interactions can also form such stars as yellow giants and sub-subgiants. And about 25% of evolved stars in open clusters go through such evolutionary tracks. So these alternative stellar evolution products are not anomalous. They simply tell another story. And now we'll go ahead and open up for questions. Thank you so much for listening.
All right, really awesome talk, Andrew. Thank you. If you want to unshare your slides, then we can get the Q&A started.
Yep.
I'm actually going to jump straight into the questions from the chat because we do have a few that were dropped while you were speaking. The first one is from Susan Dorsher. And she asks, is the rotation more important or is the mass transfer more important for why a blue straggler would be dimmer for the temperature than it should be?
So in that case, we're talking about the mass transfer. Yeah, because you're dumping all that mass, because the star's getting more massive, it will also get brighter. So if you're talking about how bright the star appears, the mass transfer is most important.
All right. And then we have another question. This is actually from Brad Munson, which is a person that you know.
Oh, hey, Brad.
How do you differentiate between blue stragglers that are part of the cluster and background or foreground stars on your CMD?
That's
your color magnitude diagram, by the way.
Yeah, that is a very good question, and one that I struggle with pretty much every day. So there are a couple different ways to get around that. So if you consider the radial velocity, so the stars in a cluster all move together. So if the radial velocity is way off from what it should be from the cluster, that's probably not a member. And you can also consider the proper motion. If you're tracking how the star moves across the sky, again, these stars are all moving together. So if you see one that's doing its own thing, probably not a member.
Okay, I have a question as well. I want to know what exactly are you studying in the context of blue stragglers?
Yes, so the particular question I'm attacking is, okay, let's say this mass transfer has happened. We've dumped all this new mass on the star. Now, if the companion star is evolved, you'll get some new elements dredged up to its surface, for instance, barium. So if you see barium on a relatively unevolved star, it couldn't have formed it by itself. So the only way it could get there is through this mass transfer. So, okay, so if we see barium on the surface of a star, about how long ago did that mass transfer happen, and how long do we expect to see that signal persist?
All right. We have another question. This one is from Rachel Malachek, who's a grad student at LSU.
Okay.
She asks, do you have a favorite star?
Ooh, that's a very good question. So let's see, my favorite star is Alberio because, I mean, it's just a really pretty star to look at, but the two stars that you do see through a telescope are not in any way related to each other. The blue one and the orange one, not in any way related. But one of those two stars is a true binary, but I don't remember which one.
I actually knew which one you were talking about because
Yeah,
that's one of those double stars that when you take someone to a telescope, you're like, here's one.
Yeah.
They're cool.
They're really pretty. That's it. They're pretty.
So you mentioned a couple times about like you don't get enough telescope time for that. Can you just explain to our audience like how telescope time works? Like how you actually get time on a telescope?
Sure. Yeah. So the way you get telescope time as astronomers, so you write this document called a proposal. So it's a rundown of the science you want to do with your time, and you're trying to convince them why this science is important to do. Yeah. So, and you're also convincing them essentially that you're not going to break the telescope, that you know what you want to get out of it. And so then they'll goes to a group of people called the Time Allocation Committee, or TAC for short, and they'll review your document and they'll say, yes, you get time, or no, get out of town. Yeah, and then however much time you request, you might not get all of it depending on who else is proposing and the time constraints of the telescope. But yeah, that's a general overview of how it works.
Is it different for you at the telescope that you use since it is semi-affiliated with Wisconsin?
Yeah, it's a little bit different for me and my institution because we get guaranteed time in this particular telescope. So if for me proposing for this telescope, it's lower stakes. But if I'm proposing for one of the big telescopes out in Hawaii, for instance, I I am competing for a very small amount of time.
Fair enough. I have another question. I got all sorts of questions because this is semi my field.
Great.
Um, can you explain sort of to our audience how you would test the formation theory for a binary star that has merged or something like that?
Yeah, for a star that has merged, so it's not in a binary, so you're not going to see its radial velocity go back and forth. But what you will see is really rapid rotation. So yeah, and that's what you might see in the optical, but you can also look and see if there's any mass loss from the system at all, like if there's a really messy explosion. So possibly I could see maybe some further follow-ups in the infrared. So I know there's been some chatter about there's a famous nova event that happened good probably 10 or 15 years ago at this point, V1309 SCO.
Oh, I know it.
Yeah. So there's been some talk about that particular event, that was a stellar merger. And so there's been some follow-ups in the infrared where it saw this big rise in brightness in the infrared, followed by a trailing turnoff. And a lot of people point to that and say, yeah, there's matter flowing out from the system. So something happened there.
Okay. Someone in the comments has a follow-up question on a
Mhm.
question that I asked. They're asking, getting telescope time is tough, but can you use data that has already been collected?
Yes, yeah, you can. Yeah, so there's some proprietary period for data that's different for every telescope. But for WIN, it's 18 months. So after that time, that data is available to the public. Yeah, so there are these archives you can find on the web where you can go through previously published studies, look at their data, and if there's something new in there, then yeah, it's fine to publish on that. It's everyone handles that a little bit differently, but in general, yes, that's fine.
Alrighty. And then I'm going to ask you a philosophical question because you mentioned, 25% of these stars are on anomalous paths, but
Mhm.
how can they be anomalous if there's 25, if it's 25% of them?
Right.
Do
That's sort
you,
of the trick here.
yeah, do
Yeah.
you think that stellar evolution theory, as astronomers have been coming up with it, is plagued by assuming everything is a single star?
Um, I'd argue yes, because it turns out, I mean, there's this old joke that gets passed around through astronomy that 3 out of every 2 stars are binaries. Yeah, and it turns out that's absolutely true. So if you're just considering stars like our sun, it turns out about half of those stars like our sun are in binaries. And the more massive those stars get, the more likely they are to be in binaries. So for the very most massive stars, like the O and B type stars, it turns out more like 70 or 80% of those stars are in binaries. Yeah, so while single star evolution is simpler, it doesn't tell the whole story.
Alrighty. Well, we have some comments thanking you for an informative presentation, and I want to thank you as well. We're going to break for intermission here in just a moment, so we will return at, see, it's 7:31 on my computer, so we'll probably return at 7:35, even though that's a bit of a short intermission. But before we do, I want to ask everyone to humbly consider donating to our Venmo and PayPal. That's how we're able to actually put on this show. And if you do, make sure in the comments that you let us know what you think about this month's tip war. So this month we're asking you if you would drink the water that was found on the moon or not. We already knew that there was water on the moon, but there's a recent discovery by a telescope called SOFIA that showed that there was a lot more water than we originally thought, and we just want to know if they brought it back, would you drink it? I think I would drink it. Would you drink it?
Absolutely would.
And by the way, last month we asked you in our tip war if you thought the phosphine detected on Venus was indicative of life or not. I told you that many astronomers were skeptical, and in fact, one set of astronomers have already written a rebuttal paper, so the mystery about life on Venus is still not solved. So we'll see you back here at 7:35, where I'll present our second speaker. And in the meantime, we'll be presenting you with some fun space trivia that you can use to impress your friends at Zoom parties.
All right.
Cool. Good talk.
Thank you.
Someone said super moon water to go with my Egyptian tomb cheese. Did someone find cheese in an Egyptian tomb?
Oh, are the super, there's a story a year or two ago of like someone opened up a sarcophagus and there was a crown like
everybody. Thank you for the introduction, Courtney, and thank you all for letting me come talk to you a little bit about the things I'm most excited about. So if you give me just a second, we'll go ahead and get started. All right. So to start off, the title of my talk is What Do You Know About Jupiter? And that's a little bit of a pun, so I feel kind of obligated to explain it. So this spacecraft up here is the Juno spacecraft. It is currently in orbit around Jupiter, and it has given us so much incredible information and some really beautiful images. So if you see a pretty image throughout this talk, odds are it came from Juno. So we're going to kind of do a whirlwind tour of fun facts about Jupiter, and then I'm going to stop by touching on some of the specific research I'm doing and some of the questions I'm trying to answer. But before we kind of go into the tour and talk about it, I'm just going to remind you a little bit about where Jupiter is in the solar system. So up here we have a diagram. It's not to scale, obviously, but we have the sun, we have the inner four planets, and then we have Jupiter. So it is by far the largest planet in our solar system. So for reference, we kind of have an idea of how big the Earth is, but 11 Earths could stretch across the diameter of Jupiter. You might know about Jupiter's famous Great Red Spot. It's about the size of one planet Earth. But in addition to that, 1,000 Earths could fit inside Jupiter. So if you basically just hollowed it out and tossed a bunch of little Earths in there, filled it up, it would take over 1,000 to fill it up all the way. And Jupiter's actually so massive that if you combine the mass of all the other planets in the solar system, it still wouldn't be as big as Jupiter. So, and that giant mass actually has a pretty dramatic effect on a lot of the other things going on in the solar system, which is a lot of what we're going to talk about. So just kind of an overview of where we're going to go today. One of the cool facts I really like is that Jupiter has the brightest auroras in the solar system. So here on Earth, you see a lot of really beautiful pictures of the aurora borealis, and Jupiter has some even more magnificent ones. Jupiter also has a bunch of really cool moons. So in addition to being an interesting planet on its own, it has some moons with some conditions that might be favorable for a good location to start searching for extraterrestrial life. So the moons are about as interesting as the planet itself. Jupiter also is really beneficial for us here on Earth because Jupiter protects Earth from asteroids that could otherwise fling in and crash into our planet. And Jupiter is so massive that in addition to kind of sucking up these asteroids and keeping them from hitting us, Jupiter's influence also creates very defined patterns in the asteroid belt that we can observe. Exoplanets are a really exciting topic right now. Everybody really likes them. We find new ones approximately every day. And a cool thing is that most of the exoplanets that have currently been discovered are really similar to Jupiter. So by learning more about Jupiter, we can learn more about the exoplanets too. Again, back to the mass, because that's kind of what makes Jupiter such a big deal. Jupiter is so massive that even though it's pretty far out in the solar system, it causes the sun itself to have a little bit of a wiggle. And that wiggle is big enough that if you were outside the solar system, you would be able to detect it. And so we're going to touch on that a little bit too. So that's what we do know about Jupiter, in addition to a lot of other things, but what we don't know is what is inside it. We can observe Jupiter from the outside, we see the beautiful storms, clouds, but we don't know what's beneath them. Is there anything you could stand on? Maybe we'll find out soon. So I start off by talking about, I mentioned that Jupiter has the brightest aurora in the solar system. And this is kind of a cool visualization of just whizzing around it. Again, most of this taken from simulations based on Juno data, but it has this really bright, beautiful ring of aurora on both its north and south pole. And so if you think about the Earth, the aurora here on Earth is caused by charged particles from the sun hitting our magnetic field and causing this beautiful aurora. And that's similar to what's going on in Jupiter as well. So we have a nice magnetic field, but Jupiter's magnetic field is the largest thing in the entire solar system. And that does include the sun. If you can consider the magnetosphere of Jupiter as a single object, it is the largest single object in the solar system. If you could see it with your eye, this is pretty much how it would appear from Earth. So it's much bigger than the full moon. And just for some context here, Jupiter would be that tiny little spot. So even though Jupiter's big, its magnetosphere is even bigger. And because you have such a strong magnetic field, you're going to get some really strong auroras going on. So I mentioned the moons as well, just kind of going to hop through it here at the beginning. But Jupiter has a lot of them. So it currently has 79 known moons, and a lot of them are pretty small, but there are 4 major ones, and these are Io, Europa, Ganymede, and Callisto. And so this grouping of moons is called the Galilean satellites, and they were the first moons that were discovered beyond the Earth. So we obviously knew about our own, ancient astronomers did, but the first ones we found since then were the ones around Jupiter. And these Galilean satellites are super cool. They get a lot of the attention for things that go near Jupiter, like you can kind of see with this little comet here. So we have Jupiter, its little moons, and there's a visitor coming, which is the Juno spacecraft. But all the attention is kind of on Europa, one of the particular moons, because it's very cool. And so we're going to talk a little bit about that in a second. But another cool thing about the moons is that if you just walked outside tonight and looked through even a small telescope at Jupiter, you could probably see them. So this is what the moons of Jupiter would look like through just a small telescope here in a backyard on Earth. You have the bright ball of Jupiter in the center and the 4 moons surrounding it. And just for size reference, this is how they would compare to Earth's moon. So they're pretty big. They're all about the same size, and some are even larger. So we're going to just really quickly touch on some cool facts from each one. So the first one, closest into Jupiter, is the moon Io. And Io is the most volcanically active body in the entire solar system. It's covered in volcanoes, and these are going off all the time. So it wouldn't be a very fun place to live. But one of the reasons that it has so many volcanoes is because it is so close to Jupiter. So Jupiter's mass and its gravity is kind of pulling on Io and causing effectively tides. It's causing Io to kind of expand, contract just a little bit. And this gravitational heating, the tidal heating on the inside, is causing these volcanoes to start erupting. And there's so many that Io actually has lakes of molten silicate lava on its surface. But if you think about all these volcanoes going off, they're spewing stuff out. And as this stuff gets spewed out, it kind of just starts orbiting around with Io. And so you end up with a donut of radiation that's orbiting around Jupiter with Io. And you can kind of see that as this hazy sulfur ring here. But you don't just have that. The sulfur then gets hit by charged particles from the sun. And so then you have charged particles again. And so these charged particles will follow the magnetic field lines around Jupiter and hit the planet. And this is kind of what causes some of those really, really bright auroras that we see are actually charged particles from Io. So it's actually this really cool system where they interact with each other. And so going from there to probably everyone's favorite moon, most people's favorite moon at least, Europa. So this is an image over here. Europa is covered on the outside with this 10-mile thick ice shell, but beneath that ice shell is a liquid saltwater ocean that is supposed to be about 100 miles deep. And so this is kind of interesting. You have liquid water, and Europa is just out past Io, so it's still pretty close to Jupiter. So it's going to have some of this gravitational effects as well, expanding, contracting. So you have heating going on inside. So you have water, you have a heat source, an energy source. These are things that you need for life. And if you kind of think of Earth, you have deep in the ocean, you have these thermal vents, and it's crazy, but there's extremophiles living there. So maybe it's not that different on Europa. And this is a place that people are really excited about searching for extraterrestrial life. So NASA actually has a mission planned for the future called the Europa Clipper, where they will hopefully go check a little further. So keep your eye out for that in the next few years. It should be kind of cool. So those are probably the 2 most interesting, but the other moons are pretty cool as well. We have Ganymede out next and then Callisto past it. Ganymede is the largest moon in the solar system, so it's larger than Earth's moon, and it's also the only moon that has its own magnetic field. Like Europa, Ganymede probably has a subsurface ocean as well, but it doesn't have as much of this internal energy. Maybe the ocean's not as promising for life as the one on Europa. Following that, the farthest out is Callisto. This has even less internal heating, but it is one of the most heavily cratered bodies in the solar system. So it's a really beautiful image for pictures. You can see this one here. It has all this texture and cool stuff on its surface. All right, so it's kind of a whirlwind tour through the moons. And now we're going to go to another thing that's present in our solar system that Jupiter has a very strong influence on, which is asteroids. So Jupiter basically can act like a really big vacuum right out there past Earth. So you maybe have things coming in from the outer solar system. These get caught up in Jupiter's gravity, whereas they otherwise wouldn't. And so if they were going to come right in and hit Earth, Jupiter can kind of vacuum them up and it protects us. So for the most part, this is good. Jupiter realistically has probably protected us from a lot of impacts. But in a couple of cases, maybe it's not so good. This gravitational pull can also take asteroids, comets that weren't going to hit Earth, were just going along their way, and kind of grab it and slingshot it directly at Earth instead. So maybe beneficial, maybe not. But a cool thing about slingshotting these things is that early in solar system history, when bombardment was a lot more frequent, Jupiter slingshotting these comets and asteroids at Earth could have actually originally brought water to Earth. We're not entirely sure, but these comets are full of water in the outer solar system, and so if Jupiter flings that water in here, it could have brought it here too. So Jupiter has a really cool effect on both these moons and these asteroids in that it pretty strongly influences their orbits. So the gravity of Jupiter is strong enough to influence the surrounding orbits and cause moons to orbit in specific patterns or resonances. So they orbit in these weird patterns where, say you have the closest in one, which is Io. For every time Io orbits once, Europa completes exactly 2 orbits. For every time Io orbits once, Ganymede completes exactly 3 orbits. So you have these really cool resonances, and it's completely caused just by Jupiter's gravity. But this doesn't just influence moons, it influences the asteroid belt as well. So this wasn't in my original diagram of the solar system, but the asteroid belt is a region of space located between Mars and Jupiter. And it's basically just this dust belt. It's full of dust, rocks, it's pretty cool. But because it is relatively close to Jupiter, Jupiter has a strong gravitational influence on it. Instead of the moons orbiting around Jupiter, now Jupiter's gravity is kind of preventing things from orbiting in specific regions of the asteroid belt. So if you look at it, you kind of have this flat plane of asteroids and then these very clear, well-defined rings in it where nothing can orbit. And that's due to Jupiter just kind of pushing them out. And so these are called Kirkland Gaps. And it's really incredible how sharp and well-defined and easy to see they are. And it's also pretty incredible that Jupiter just has such a strong influence on everything else in the solar system. And this is just kind of a video again showing that. The green here is your main asteroid belt. You have Jupiter orbiting on the outside and this triangle of asteroids orbiting in a pattern on the inside. In addition to that, Jupiter kind of acts like a shepherd and pulls 2 groups of asteroids around with it in its orbit. So these just one leads ahead of Jupiter and one trails behind it, and they just follow it as it orbits around. So just kind of shepherding all the asteroids in the solar system. Hopping from there to a different topic, which is exoplanets, kind of a very popular one right now. But most exoplanets that have currently been found are similar to Jupiter. As of early this month, 65% of all confirmed exoplanets so far are Jupiter or Neptune-like. Now, kind of a little bit of a question comes up here. Are these found most often because they're the most common types of exoplanets out there, or are they found most often because they're the easiest to find? And they would be the easiest to find because they're big. And so like I mentioned earlier, Jupiter is so massive that it can cause the sun itself to wiggle. So if you have 2 bodies that are orbiting, you can kind of think of the Sun-Earth pair to start. They actually orbit around a common center of mass, but the sun is so much more massive than the Earth that that center of mass is basically at the center of the sun anyways, so the Earth just orbits the sun. However, if you think of the Sun-Jupiter pair, Jupiter's pretty massive now, and it's not really negligible. So now the barycenter here, or the center of mass, is actually located 30,000 miles above the sun's surface. So both the sun and Jupiter actually orbit this specific spot in space. And so what that's going to look like is this. You have the sun moving in a little circle. And as this sun moves, the light that you're going to measure from it is going to be Doppler shifted, which I think we just heard a little bit about the Doppler shift. And so as a light producing source moves towards you, the wavelength is shortened, it's bluer. As the light producing source moves away from you, like you see here, the wavelength is extended and it's redder. And so this is actually how we find a lot of exoplanets, is by measuring the shift in light caused by the star kind of wobbling like that. So keep this Doppler shift in mind. It's actually going to be a pretty important topic for my specific research that I'm going to touch on here in a second. It's just kind of an interesting one in general. To conceptualize it a little bit more, this doesn't just apply to light. The Doppler shift applies to sound as well, and you may have experienced it yourself if you're standing on a sidewalk and an ambulance with its siren going by drives past you. So as it's coming towards you, the siren's going to be more high-pitched, and then the siren will pass you and it's going to get lower pitched as it drives away, and that is the Doppler shift when it is moving towards and away from you. So the really interesting thing about all these exoplanets that we find being similar to Jupiter is that we can learn about the exoplanets by studying Jupiter. It's closer, it's easier to see, and it's easier to learn about. These exoplanets are going to be really, really hard to determine specific things, so we use Jupiter as a way to learn about them. And so that brings me to the first big question that I really want to answer. So you see this video here, this is a simulation of flying into and then back out of Jupiter's Great Red Spot. And this is what we see when we look at Jupiter, and what we know about is it has these layers and layers of clouds, this really thick atmosphere. As you get deeper in the atmosphere, it gets hotter and the pressure increases. So my question is, what is beneath that? If you're anything like me, you may have wondered, is there any surface anywhere within Jupiter that I could stand on? You know, The temperature is going to be really high. The pressure is going to be really high. But if your body could survive those, could you stand on anything or would you fall all the way through it? And so the first question I really want to answer is there a solid surface within Jupiter? Does it have a core? If it does, what is that core like? And it's kind of crazy to me that we still don't know that. There's so much we know, but there's so much left to learn as well, even within our own solar system. So I mentioned that Juno is in orbit around Jupiter. It's giving us a lot of really cool information, letting us learn a lot about the planet. And one of Jupiter's main goals is to actually try and figure this out. What does the inside of Jupiter look like? So as Juno is orbiting, it can kind of measure this through Jupiter's gravity. So if the interior structure of Jupiter changes, maybe some areas are more dense, this is going to cause the gravity above that specific location to change as well. So as you have variations in the internal structure, you also have variations in the gravitational field. So instead of traveling on a perfectly circular orbit, like you would see here as the blue line in this diagram, the orbit's actually going to change just a little bit. And these little wiggles are caused by the gravity from the planet causing the spacecraft to act slightly differently. So we can use that, the little wiggles of the spacecraft as it orbits, to kind of infer what the interior of Jupiter is like. So it maps this on very close orbits. But the problem with this is it can only probe so deep. So measuring the gravitational variations on Jupiter can give us really good information about halfway in. And then we can't get any more information after that. So we can't probe all the way down to the core using these gravitational moments. Even though we can't probe all the way down to the core, we can use that to get some idea of what it's like, because we know what it is on the outer layers. So people can make models and kind of best guesses as to what the core is based on what the outer layers are. And the current leading theory is that Jupiter does have a core, it does have heavy elements, but it's fuzzy, it's not well defined. So what they think happened, this is the current leading theory is that Jupiter originally had a solid rock ice core in the center. And in the early solar system history, this was impacted by another rock ice body. And this impact kind of broke up the core. And now, instead of this solid thing with a well-defined boundary, the material kind of settled back in and you have a fuzzy core. And this is what the current, what fits the results. And so with that, this is what we think the current internal structure of Jupiter looks like. You have the thick atmosphere of the hydrogen and helium gas. You move a little bit in further and the pressure increases. Your gas is now going to transition to liquid. So you have a layer of basically liquid water in Jupiter. So by extension, Jupiter does have the largest ocean in the solar system, which is a little weird to think about. But if you keep going in, pressure is going to increase anymore. And now you get to a really weird state of hydrogen where it's not gas, it's not liquid, but instead it's metallic hydrogen. And so that's going to compose a lot of this region. You have this metallic hydrogen. And then at the very center of that is where we think that diffuse fuzzy core is. But okay, so we kind of know what it is. How do we actually learn? How do we really measure down in the center? So one of the leading scientists right now on the Jupiter interior structure says that he doesn't foresee another leap in knowledge about Jupiter's interior after Juno unless we're able to study the planet's internal oscillations like people have done for the sun. And so to kind of back up a little bit and talk more about that, that's just talking about seismology, which is a relatively familiar concept. We used it to map out the internal structure of the Earth. So on the Earth, you have earthquakes that occur, and these are going to generate seismic waves that travel through the interior of the Earth. And these waves will travel differently through different materials. And so if you can measure these waves, you can measure how they traveled, and then that lets you kind of map out the different density structure. So we know the Earth has a crust, has a mantle, has a liquid outer core, and a solid inner core, and we're pretty confident about that. So if these techniques work so well for Earth, how do we apply them to other bodies? And astronomers have very successfully applied these similar techniques to the sun, kind of building a new field called helioseismology. And so on the sun, you don't quite have earthquakes, not in the same way we do here, but you have convection going on. So you have hot gas rising up and cool gas crashing back down. And when this happens, it generates acoustic waves, sound waves. And these waves are going to bounce around through the interior of the sun in specific patterns, which we call modes, but it's basically they just bounce around in these patterns. As you can see in this video, some are going to kind of bounce around near the surface, some are going to go a little bit deeper through the center. And these sound waves, again, travel different through different densities. They will actually travel faster through higher densities, slower through lower densities. So if you can measure them, you can get an idea of the actual density. It's a little complicated. You can kind of think of this like ringing a bell, right? Sound waves, but because convection is going all over the sun, you're not just like ringing a bell in one specific location. It's kind of like a bell in a sandstorm. It's being hit on all sides. You have this going on everywhere, and it's kind of complicated to pick out the specific ones you want to see. But it's been done, and it's been successful, and we pretty much know what the inside of the sun looks like. So as these waves bounce around, they basically hit the surface, and they cause the surface to move in and out, just slightly, which you can kind of see in this image here. So you have the waves going through, causing the surface to oscillate in and out, and this surface is what's producing the light that you see. So now you have something that's emitting light moving towards you and moving away from you, which means you have a Doppler shift. I mean, it's a small one, but it is there, and it can be measured. And so if you measure this Doppler shift, you can get an idea of the waves that caused it. And then if you measure those waves, you can get an idea of the material traveled through. But these are really small signals. They're pretty difficult to detect. And in order to detect them, you need really, really long-term observations, and ideally observations that aren't broken up. So that was the sun, but Jupiter and Saturn really aren't all done. There are planets which we see in the belts and the zones of Jupiter, so the hot gas rising up, cool gas crashing back down, generating sound waves and going through the planet. So theoretically, we should be able to make the same measurements on Jupiter and Saturn that we did for the sun. But like I said, you want these really long-term observations to do it, hopefully not broken up. And so that's what I am personally trying to do for my PhD. So I'm working on actually building a telescope to detect these oscillations. You see a telescope in these top upper images here, and we actually did build this from the ground up, so it's kind of cool. There's the front view. It's encased in this carbon fiber housing. You actually see some blue insulation in there, and then the instruments on the back. And then this bottom image here is me and some of the team that worked on this telescope, and we're actually in a deep freezer with the telescope in that picture, which I'll touch on here in just a second. But I first want to show you the instrument package on the back, which is over here. And it looks kind of complicated, but we have 3 different instruments. And so this is just a model, but it does exist in real life as well. And it does work. We've collected observations with it, and I'm going to show you those too. But the main reason we're in a deep freezer is because I said we want uninterrupted observations. If you want to stare at Jupiter for a really long time, it's kind of hard to do that from almost anywhere on Earth, because your night is going to be at most 12 hours long, and then the sun will rise, and you have to stop observing until nighttime. But there are a few places on the planet where that doesn't happen, and one of those is the geographic South Pole, which is well established as a place for astronomy. And at the South Pole, you have one sunset and one sunrise every single year. And so during the nighttime, instead of rising and setting, your stars are basically just going to orbit in the same location in the sky, or the same height at least, and so you can just stare at it, theoretically for 6 months straight without any interruptions. And so that is the end goal for my project. That's why we were in a deep freezer, trying to make sure our telescope could run in cold environments. That's why it has a lot of insulation. But the South Pole is kind of difficult to get to. It's kind of hard to run an instrument there. So there's a lot of preliminary work and testing to get done. So although that's the end goal, we're not quite there yet, hopefully one day. But what we're doing right now, and why I'm currently in Hawaii, is because we just used that instrument that I showed you that we built up to collect about a month straight of observations on Jupiter. So what you see here on the screen is basically what I saw for 12 hours a night for 24 nights straight. So it was a pretty rough time, but it was pretty cool. So this is the whole team. We were just up all night long, and I'm here in the red image. You can kind of barely see me. But it was a lot of work, and we collected some really pretty data on Jupiter. So this is through the instrument we built. It's 4 different images of Jupiter. They're all about the same. You can just pick one and look at it. But you see a bright dot, and that's actually the moon Io, that volcanic one that I just talked about. So not only can you see Jupiter, you can see the moons, and then the little black dot below Io is actually the shadow of the moon on Jupiter's surface. So it's really exciting and really rewarding to see like an instrument that you've been able to be a part of actually take these images. And so I'm going to tell you just a little bit more about the 2 instruments really briefly. This gets a little less fun to talk about, so we'll kind of skim over it. But there are 2 different kinds of instruments on this telescope. You don't just quite take a picture of Jupiter like you normally would. One of our instruments is called a Doppler imager. So this is just trying to image that Doppler shift that I told you about. And so we just look at one specific absorption line. We have 2 of these going on, so we get to look at 2, but we'll just think about one for right now. So you have the light, you have one absorption line. And as this line is Doppler shifted, it's going to shift left and right. So you basically have 2 little bitty probes, which you see as the red and blue here. And these are going to measure the intensity of the line. So as the line shifts, the intensity in one probe will go up, the intensity in the other will go down. And this is actually how they did helioseismology and how they were able to map out the internal structure of the sun. So we have 2 of these Doppler imagers that we've built up and collected data on. This is actually what our data looks like. My sisters like to laugh at me because unfortunately we take these really pretty images of Jupiter that you see over here on the left, and we just basically get rid of all of the Jupiter. So you take the pretty images, make them look not so good, but then you can get some science out of them. So basically what you see is this one dark band, and this is the only place on the entire disk that you can measure just that little shift of light. So it's pretty difficult to see. We're working through it right now, so hopefully we'll have some results sooner rather than later. But our other instrument is a polarimeter. So you may have heard of polarized sunglasses, and they block glare when you see it on the water. And so similar technique. So when light reflects off of a surface or scatters through some particles, that light ends up polarized, which means it's basically, in a weird way, all pointing in the same direction. And we're trying to measure the reflected sunlight off of Jupiter. So it basically hits Jupiter, scatters off the particles, reflects back to us. So this light should be polarized. So our other instrument is a polarimeter, and it's going to measure this light. And so this can kind of help us. We have an independent verification of any detections we might make with our Doppler imager. And this is also sensitive to the whole disk. So now we don't have to just look at that one little slice, we can look at the whole disk. And this also lets us watch other cool things that may happen on Jupiter, such as moons transiting it, storms developing. There's a lot of cool stuff that is probably in the data we just collected that we're excited to find more of. And so with these 3 different instruments, the data set that we just collected, so about a month of data, and then hopefully some future data at the South Pole, we think we have the capability to find out what is inside of Jupiter. And then if we can find out what is inside of Jupiter and what its core looks like, then we can use that to maybe answer the final big question I'm really interested in, which is, how did our solar system form? And I know that seems like a big one, but hear me out. So there are currently 2 different competing models for solar system formation, and the more common one is the core accretion model. This is, you have a central star, you have a disk of dust and gas, and little bits of dust will orbit, stick to other bits, and grow. And as they grow, they get more gravity, accrete more material to them, and the planets kind of build up from the bottom. So if we can see what's in Jupiter, and Jupiter has a solid, well-defined core, that's going to lend a lot of strength to this core accretion model. However, there's a competing theory, and this is the disk instability model. And this is that, again, you have the central star, a disk of material, gas and dust, and overdensities in this gas and dust can kind of collapse down on themselves and form into planets, similarly to how stars form themselves. So as of right now, we don't really know which one of these is the case. And what is actually inside of Jupiter will lend a lot of strength to one of these 2 theories over the other. So that is the 2 major questions I'm trying to answer. Hopefully we'll get there one day and you guys will actually be able to find out what's inside Jupiter along with me. So I will leave you with, this is actually a video of every single image that we took over that month-long observing run, and I'm happy to take any questions.
Thank you so much, Deb. You did awesome. You want to unshare, then we can start the Q&A.
I gotcha.
Okay, so as the MC, I get the honor of asking the first question. How much did you have to know? So you built a telescope. Like, how much electrical engineering did you actually have to know in order to build that? Because astronomers are not known for their good wiring skills.
Right. So I actually came into this project a little late, and thankfully there are a lot of people on this project that are much better than me at engineering, so they handled most of that, but they've been really good at teaching me along the way. So I came into it knowing none. I still don't know that much, but definitely more than I did. So it's been really cool actually getting to like develop a whole new skill set as it's going on.
Cool. So we'll start fielding questions from the chat. The first one is from Rachel Malachek. She asks, how does Europa keep its frozen layer while being relatively close to Jupiter?
Hi, Rachel. So Europa, even though Europa is relatively close to Jupiter, Jupiter itself is really cold. So you can think of on Earth, right? As you go higher in altitude, higher in elevation, it gets cold, the air gets cold, right? And so the outer layers of Jupiter are just clouds, which are ice particles and stuff. And Jupiter is much farther away from the sun than the Earth is. So it's actually not like getting or emitting all that much heat. So it's pretty cold almost everywhere. I guess probably not right on Io with all the volcanoes. and the tidal heating that you get as an effect from Jupiter is going to affect it pretty deep down. So it'll keep it liquid in the center, but the core out there is still exposed to space is still icy and cold.
Okay. Our next question is from Tyler Ellis, who's one of the AIT staff, and he asked why you chose Antarctica for your telescope when you could have used some optical interferometry like Chara.
Okay, so it's funny, GSU actually, GSU uses Chara a lot actually, which is pretty cool. But the main thing is that so we really want to be able to use these magneto-optical filters because they've been successful. Historically, people have tried to use interferometry to measure these oscillations. And also, I mean, Chara is it's a pretty big, well-known telescope, right? So it's difficult to use anything like Chara or a space-based telescope because you really need these long observing runs to measure it because you're trying to measure these small signals. So it just, even though I go to GSU, which uses Chara regularly, it would be really difficult to get as much time on Chara as we would need to actually make these measurements.
Good. The next one is from AP Mad Scientists, and he asked, was it the moon Ganymede that had its own magnetic field? On a relative scale, how does that compare to the field on Earth?
Ooh, so Ganymede does have its own magnetic field, which is pretty cool. I actually didn't, before I was putting this talk together and learning facts about Jupiter on my own, I didn't know that any of the moons had a magnetic field, so I was pretty excited to learn that. I don't really know how it compares in relative strength to Earth. I imagine it's going to be pretty significantly weaker because Ganymede is going to be a lot smaller than Earth, and it's a good question. I imagine it's much smaller than Earth's magnetic field though, but it's pretty cool to learn about that it has one.
So I gave a talk once about auroras, and I read that Jupiter's auroras actually connect to one of its moons. Is that true? Or is that just one of those weird Wikipedia things?
No, that is true. It connects to Io. So Io is emitting the sulfur particles, and these turn into basically charged particles that get funneled onto Jupiter's poles via the magnetic field, which helps create those like insane auroras.
Very spooky. It's an extremely spooky effect. Our next question is from Clarissa Morales, and she asks, have these quakes on Jupiter been measured by anyone before?
So people have been trying to measure these for about 20 years now. So we're definitely not the first people to try it, but they have not been definitively measured by anyone. There's some promising results from some people a couple years ago. So we're kind of using those as a baseline and hoping to build off of the really cool work they did. But it's kind of a tough thing to do, which I guess is why it hasn't been successful yet. So keep your fingers crossed for me.
Our next question is from Susan Dorsher, and she asks, are the disk instability model and the collision model incompatible in their predictions, or are they different ways of mathematically solving the same problem?
So I imagine that they are not incompatible. So realistically, the disk instability model explains the inner planets really well, right? Mercury, Venus, Earth, Mars, these don't really work with the disk instability model if you think of just gas and dust collapsing down. But also, the outer planets don't really work with the core accretion model. If you simulate it, there's really no way that Jupiter and Saturn should be able to accrete as much hydrogen and helium as they did before the sun blows it all out of the solar system. So I don't think they're mutually exclusive. We clearly really don't know which one is right, but if I had to guess, I kind of would imagine that it is some combination of both is actually how the solar system formed.
That's usually how astronomical theories work, so it's usually just both. It's both.
Yeah.
So I wanted to ask you, you applied to be an astronaut, right? Can you tell?
I did apply, yeah.
Can you tell people about what that was like? I know that the results don't come out for quite a while, huh?
Yeah, so the results don't come out for a while, and I kind of, I've heard that you have to apply over and over and over again, basically, to ever get selected. So I just figured I would get a head start and start applying now. But yeah, it's obviously a super competitive field. That's a lot of the reason why I really wanted to go to Antarctica, to live and work in kind of a harsh environment. I thought it might help the application process. But it was kind of cool application. Realistically, you just submit your resume, and actually starting this year, they started this new, I don't know if you would really call it a test, but you get on and you answer a bunch of personality questions, like how would you handle this situation questions? What would you do if this was the case? And so the application process was relatively easy. It's just submit your resume and answer a bunch of questions, and then I guess keep your fingers crossed and hope luck
Wait
is on it.
forever.
Yeah.
And just pray.
Yeah.
Jen Little is asking, is this like a new space race to find out Jupiter's secrets, or is everyone more or less working together and sharing their information?
Yeah, so it's a pretty good question. It is a ridiculously new field and a ridiculously small field. So there are realistically maybe two major groups trying to do that, and we're one of the two. There's probably a few other smaller ones spread out through there. And we have some members on our team are also working with the other group. And we're definitely hoping to collaborate more in the future. The other group, the one that I actually just mentioned, has some pretty promising historical results, but they're not definitive yet. They may have actually collected some observations at the exact same time we did. So it'd be really cool to kind of compare what we get with what they get. We don't have a collaboration going yet, but it would be fun too. Although I guess we can also have a space race to figure out what's inside Jupiter. That'd be cool too.
Is it really a space race if it's not against Russia?
Okay, true.
Susan Dorsher also asks, is the South Pole crowded yet?
South Pole crowded yet? Gosh, I guess the summer season is just opening up, so it's probably gonna get about as crowded as it can soon-ish. I imagine, or well, I guess I know that COVID had a pretty drastic effect on people getting to go to the South Pole this year. I was supposed to go. Clearly, I'm not there, so some people who were supposed to go didn't end up getting to. So it's probably a little less crowded this year than it has been in previous years. But I've heard that the summer months down there, when it's daytime all the time, actually get relatively crowded. And so again, they only have a specific number of rooms, a specific amount of food that they can feed people. Over the winter months, when I was trying to go, it is the opposite of crowded. So there's maybe 30, 40 people there that you see for the entire winter. So it's probably moving towards getting crowded right now.
All right, and then we have one last question from our chat. Is any of your preliminary data classified? Would you have to kill us if you revealed something?
I don't think I can share any of it yet, so maybe.
You would have to kill us? Okay. I was not expecting that answer.
No, I'm kidding. I wouldn't have to kill you guys, but
we also did have a talk once from Arlo Landel, who actually talked about his winter at the South Geographic Pole, which is actually like
oh man.
talk. I don't know if we have a recording of it, but if we do, it's on our YouTube. So before we head out, there's just a few. I want to bring both of our speakers back on. So if Andrew could come back on, I think the stream will still work. All right, we have a tradition here at Astronomy on Tap in Baton Rouge, and that is to ask a certain question from a certain someone who is Tabby's son named Jude, and he wants to know, what is your favorite Pokemon?
Ooh, Squirtle. Mine has to be Squirtle.
I'm gonna have to go with Jirachi. It's always been my favorite. It's got a little star head. I like space.
Oh, I know which
Space
one.
baby.
Oh yeah.
So
we always have to ask. We always have to ask. I want to thank both of you very much for speaking today and volunteering to come give a talk with Baton Rouge. We know you're both really busy, but we're really thankful to have both of you. I want to also shout out our two streamers, Allie and Alex, who are behind the scenes. They work really hard to put this show on for us, and you don't see a whole lot of what they do, but they do a lot. And before we head out, just a few other things I want to mention. If you're watching us asynchronously and not live, feel free to still interact with our video. Leave a comment, like the video. That bumps us up in the algorithm, which lets us reach more people. Reach out to our social media, anything you want. We'd love to hear from you guys. Feel free to subscribe to our channel to get notifications for our next show and help us reach 100 subscribers. That way we can get a unique YouTube link and we don't have to keep putting out just like numbers at the end of a YouTube link. Maybe we can make it say AstroTap BR or something like that. Also, please consider donating if you feel free. If you want to, our links are both in the YouTube chat. And let us know in the comment of the donation whether or not you want to drink the water from the moon. Are you guys drinking from the water from the moon? Yeah, they both are. I mean,
absolutely.
I am too. So keep an eye on our Facebook, Instagram, and Twitter. We post all information about our events as soon as we have information. And we'll see all of our viewers next month here on YouTube, where we'll have 2 more lovely speakers. And then everyone have a lovely Thanksgiving. Everyone is contractually obligated to wave like a Muppet now.